start this. Okay, was there any housekeeping? Oh yeah, the lab section, right? I booked us that room for the hour after class. And so after class, we'll just head over there. It's in the H building. And so, and then we'll have our hour of extra time, right? Call it a lab, call it whatever you want, right? It'll just be kind of extra time, but more time for you to work on things, right? And just kind of maybe work on the labs, or I'll give you a couple of little itty bitty exercises as an assignment. Man, oh man, love the sunshine, but I'll get distracted. So the adjusted R squared is so right, and so our lab this weekend for every other week right after this, but our lab will be in H116A. From 11, that's when we get out of here, right? 9:30 to 11, well, 10:50, whatever. From 11 to 11:50. It's just a 50-minute blip. Blink and you miss it. So you feel bad because I feel like I forgot to tell you guys to bring your laptops, but you did. Good. Hey, 10 out of 10. Big day. You guys like showing up on Mondays, I've noticed. It's like Mondays, everyone's here. Wednesdays, not so much. Fridays, definitely not. No, most of you are here. So that's why we're doubling down on Mondays. Have that little lab section. Okay. But we'll just call it extra time, whatever. Just on Mondays, right? So I'm just taking that 50 minutes on the Friday and just moving it to right after this class on Mondays, right? So we get the worst of it over on the Mondays, and then it's easy straight from here on out. Or at least for this class. I don't know about your other classes. Yeah. Okay, so chapter 3, we're going to split across the 2 days. I don't know, how much multiple regression have you guys talked about? None? Okay, that's what I assumed. And then I was like, oh shoot, I should have asked them on Friday how much you've done. Okay, great. So multiple regression. Right now, right, simple regression is when we only have the 1x. And so simple regression is when we have one predictor variable, right? And so our model is going to look like y hat is beta naught plus beta 1, beta 1 x. Used to always throw me for a loop, capital Y's, lowercase y's, but often what we do is we use the uppercase x's and y's if we're talking about the population, and then lowercase if we're talking about the sample. And so sometimes I'll slip up and I'll still use lowercase for the population, but you'll know it's the population because of the betas, right? And so either way, it doesn't really matter. But I think the textbook uses that convention of capitals for the population and lowercase for the sample. So, so now we're just going to add more values of x, right? And because we understand that, well, looking at how y is affected by one thing, Sure, sometimes that makes sense, right? We talked about the price of a Honda Accord, right, or Honda Accords. How is it related to the mileage? It's reasonable to say that it's probably related to more than just the mileage, right? And so we want to be able to incorporate things like the age, right? Maybe if it's been smoked in or not, right? We can have binary variables like that in there. We could have things like, is it from the States, right? Those are usually a little bit cheaper than the ones from Canada. What other things can we talk about, right? So there's lots of other things that we could talk about that we want to incorporate into our model, or at least see if they would help us get a better prediction for the price, right? And so often there are more variables that might help explain changes in the response variable. Changes in the response variable. So now we're building the same kind of model. I guess I should throw on the error term up here. I usually kind of drop it. We know that our model is going to have, oh, population doesn't have an error term. Sample has an error term. So now, if we want to have more than one predictor, right? So more than one X, our model is just going to extend a little bit and say, well, we're still going to have some intercept, and then we're going to have B1 X1 plus B2 or beta 2 X2 all the way up to beta K X sub K. Usually I write my K as kind of as a cursive K. That's why they look a little sing-songy. Should rewrite them though. Where we have K, oops, K, or I'll put in brackets, usually I write my K like that, K predictors. Often what we'll do is, because we can't look at, well, we could look at a 3D plot, right? But that's going to be kind of hard even to wrap our heads around. And that only leaves room for X1 and X2, right? And then Y. So it doesn't leave room for K predictors, right? And so we would have to have a K plus 1D plot, right? So it doesn't work. Or maybe just KD. Anyways, doesn't work. So what we do is we look at the scatter plots between the response variable and each of these predictors, right, in order to see which one is maybe going to help, right? And so we usually look at scatter plots of the response variable against each of the possible explanatory variables, And this is to try to figure out which ones should we start by including in our model, right? If we see something, so if we have a variable in there, something that really doesn't affect the price, right? Who could it be? Or what could it be? Almost everything could affect the price of the Honda Accord, right? So it's kind of hard to think of something. But maybe something weird like the VIN number, right? We could have a categorical variable of the VIN number. Each of them is going to be in its own category, so it's not very useful information. In fact, I would probably just toss it. But obviously, we wouldn't want to use the VIN number to try to predict the price. It doesn't really make sense, right? So something like that. I'm drawing a blank. I can't really think of any other variables that wouldn't potentially affect the price. So what you do is you plot your response variable against each of the possible explanatory variables. And the ones that have some sort of relationship, right, whether that be linear or nonlinear, if you're able to transform it, right, you could still use a transformation in there. We won't get there today, but next day we'll look at, okay, well, I could have x's in there that are transformed, that's fine. And so we usually look at the scatter plots and just to figure out which ones could be included in our model. Against each of the possible explanatory variables to determine which predictors might be included in our model. Once we've done this, right, we looked at how do we find the slope and the intercept, right, of a simple linear regression. We're not going to do that, right? Of course, we're just going to use software from here on out, right? And so we'll dissect the software, right, the software output, because that's what we need to know what it's saying, right? And so if I steal, because I'm special and I have a copy here. Where was it? Here. So I'm kind of assuming that you've read sections 3.1 to 3.3, but just as a quick reminder, run through, because I really, really hate it when people have assumed that I haven't read it. It's like, oh, you haven't read this, so you won't know this. It's like, I actually did read it, but also, if you haven't read, it's fine, whatever. So, typical multiple regression output, if we're fitting the line, so here, this is talking about, and I am not very good with sports, and so I think, NFL, which I'm just breaking down NFL, I think is football. So here we're talking about football. The beauty of stats is you don't really need to know what you're talking about, right? I can just have the data, I can look at the columns, I can fit models, I can model things, I can predict things. I do not necessarily need to know what these things are, right? Some background usually helps, right? So here we're talking about, so they've got a bunch of teams, and so they've looked at the points for and the points against, and so how many points they got versus how many points others got on them, I'm assuming. So something like that to predict their winning percentage, right? And so, so what we've got is, if we look at our output here, in R, we just had the linear model against, so y tilde x, right? Whatever our y was, tilde our x. Now you can just say x1 plus x2, right? So for example, because my laptop's having a nap, right? It's not very efficient here. I know. I use the equal sign. Do you guys use the equal sign or the arrow? I know, you're proper. I know, and I should have been too. I got into a lot of trouble with my supervisor, but I just like the equal sign. And there's actually very rare instances where the equal sign gets you in trouble, so I'm just gonna keep doing it. Now I can't even remember, is the arrow going this way or that way? That way. See, that's how little I care for the arrow. It's 2 keystrokes instead of 1, guys. I know, you're proper. That's good. Stay that way. Stay innocent. It's good. So now, right, if we were just looking at a linear model command, right, we wanted let's just call it NFL. Of course, this isn't going to be proper because I think the NFL data has a different name, but let's just call it NFL. $, win percentage, or point count, or I actually don't know what it stands for, and it doesn't matter. Against maybe the points for, so the NFL $ points for, right? If I move this down a little bit, this is simple linear regression. And then if we have multiple linear regression, right, you can call it mod 2, is the linear model of, again, NFL win point count or percentage, I don't know. And then against NFL points for plus NFL $ points against. Come on. Squeeze it in there, sorry. So messy. Way nicer if you type it. Okay. So you're allowed to just add on more predictor variables. Right? And so here, what you get is you get output that looks like this. And so we have seen output that looks like this with just the last line missing. That's fine, right? Simple. And then now we're going for multiples, right? Now we've got multiple predictors in here. It still gives you the coefficients, right? And so each x, right, including the intercept, is going to have some coefficient, and we just pull those from out of here. One thing to keep in mind about these coefficients is this is how a change in points for example, right, a unit change in points for is affecting the win point count or whatever. Yeah, whatever, right? And so it is assuming, though, that the points against are just staying where they are, right? So it is kind of saying that, okay, well, this change, right, is assuming that nothing else changes, right? So if I'm only changing the points for, this is how it would impact my win point count or my wins. let's call it wins. Then I don't have to bother with it, okay? And so same thing with the points against, right? If I'm holding the points for steady, then a change in the points against then would look like this. These are really small numbers. That's just for this case, right? Because I am assuming that 1 point over a bunch of games isn't that, like, we're talking 50 points. That's going to make a difference, right? 1 point isn't going to make a difference, right? And so it's just the scale of the data. It's not, doesn't mean anything, right? And so 1 point isn't going to affect your wins significantly, right? But if you look at the p-values for each of these, right, the p-values are approximately 0 for both. And so that tells us that individually, these things are both contributing to our model, right? And so here, let's see, to match my shirt here. Both predictors contribute significantly to the model. Okay. That's the same as saying that their slope individually is significantly different from 0, right? And so they're contributing to the model, and they're not just adding a 0 slope, right? We can do +0, +0, +0, +0. It's not going to affect our model, right? And so you can have these predictors in there that don't actually contribute. And later on, right, we'll talk about what we do in that case. But for now, we'll just leave them in.
So let's say if we have 3 variables,
Mm-hmm.
by the multiple regression, and the third one is like 1000001
Mm-hmm.
or something like that.
Yeah.
So can we eliminate that thing and just create a model with the other two? Or
do you mean the coefficient is really small or the p-value is really small?
Significant coefficient.
So, yeah, like are you saying this value here, if we had a third one, would be really small?
Yeah, because those we put it into our model.
Right. Mm-hmm.
So
because these are on like the 3rd decimal,
yeah.
let's say, and you're saying this one might be on the 5th decimal?
Yeah.
So I know that's not proper terminology, but I think we all get it. Right, and so we've got this tiny one. It would still depend on the p-value over here.
Okay.
Right? If that's the case, it's likely that it wouldn't be significant, and then we could probably remove it. But not necessarily, it can be significant. So we go based off of the p-values.
So the standard p-value you're comparing is 0.05.
Yeah.
9%.
Yeah. Let's just use 0.05 for the rest of our lives. Unless, if you're talking about something that maybe costs you $3 million, probably make it a little bit lower just to be sure, right? It just depends on the costs, right? And so then you can make it a little bit lower. But in this case, right, we would be safe in either sense. So, okay. So we talked about last day, we've got our R² and our adjusted R². In the simple regression, right, in our simple linear regression, where we only had 1 x and 1 y, then we said, well, these two doesn't matter which one we use, right? But then we also said, you know what? For multiple regression, we're going to use the adjusted R². And so this R², unlike the let's call this kind of 1. Unlike the simple linear regression, the straight up R² for multiple regression, because for simple regression, it was just the correlation between x and y squared, right? But now you've got 2 x's, so how are you supposed to do that? Right, the R² for multiple regression it's actually going to be the correlation between the fitted values against the actual values of y squared. Okay? And so our r squared in multiple regression is the correlation between the fitted y's and the actual y's squared. So it's a little bit different from our usual r squared. But like we said last day, well, if we're talking multiple regression, we should be looking at the adjusted r squared. And so for multiple regression, we should use the adjusted r squared to assess the fit of our model. To assess the fit of our model. What the adjusted r squared is doing, right, is if we go back to this example where if we have a ton of variables in here, each variable that we add, right, so each predictor that we add will increase our r squared, right? It will make our model better. Okay? The problem is that is it making it significantly better, right? Or are we just adding in things and it's not really capturing any of that variation in the y's? Right? So that's what we need to kind of be wary of, because we don't want to overfit our model. Right? We don't want to have too many predictors in there. In fact, we usually want to drill it down to as few predictors as we need, right? So not more than we need to get a pretty good prediction out of this thing, right? And so the adjusted r squared, it looks at the trade-off between adding another predictor and what's the decrease in the errors, right? And so it looks at, okay, well, adding that predictor, did it decrease the amount of variation, right? Or did it capture more variation? Or did we not really capture any of that variation and we added another predictor, so it's adjusting for the number of predictors in our model?
So let's say, for example, you have 5 predictors, and all of them are significant. So how do you...
If they're all significant, then they should all be there, right? It's possible that one might be a multiple of the other, right? For example, if we're thinking about the mileage and maybe the age of the car, right? Those are going to be increasing together. And so it's possible that we've got that relationship that we need to kind of untangle first, because it's possible that they're both significant in predicting the price, right? But if we remove one, right, our model might still be pretty good, because the one of the predictors is just taking over so if we keep the mileage in there and get rid of the age, for example, right, then maybe the mileage is able to compensate for the age variable. And so sometimes we need to keep an eye out for predictors that might be related to each other. Does that kind of make sense? So sometimes you're going to have significant variables, but you also want to talk about, okay, well, what if I pull this one out because I think they might be related? Yeah. But you can see that in your scatter plots, right? Because if you've got explanatory variables that have a linear relationship, right, then yeah, you can add them both into your model, but then maybe take a step back and say, well, what if I remove this one? Is my adjusted R squared, is it going to improve or significantly, right? Is it going to jump up a lot? Because I've got an extra predictor that I was able to pull out, right? So
we stick with the R squared 75.
I would say it depends on the situation.
For the
Oh yeah. So for this one here, I would report the 76.74, right? These are pretty similar,
yeah,
so you could go for either one.
Let's say a standard value
Not really, because again, it depends on how much of that variation you're expecting to be able to predict, right? And so if you're expecting this huge kind of wide, let's call it a wide relationship around your around your line of best fit, then maybe an R squared of 0.5 is really good, right? Because you've got this variability that you just know you're not going to be able to capture that, right? Whereas if you've got something that you're expecting to be really tight, then an R squared of 0.5 is not good. So it just depends on the relationship that you're talking about. As kind of a threshold, I would say probably 0.6, 0.7 R squared is pretty good. That depends on the situation though, right? And also, I mean, if you've got an R squared of 0.6 with only one variable in there, that's really good, right? But if you've got an R squared of 0.6 with 14 variables in there, that's really bad, right? And so it just depends on, it's kind of a guessing game. And it depends on what you're talking about and also how many predictors you've got in there.
to identify which variable to remove, we have to draw a scatter plot with respect to that variable and y every single time.
Yeah.
So 14 scatter plots and make sure which one is looking good.
Yeah. Yeah. And so so this is where stats kind of transitions from being like straight rules and math and stuff to being more of an art where we kind of go in and we adjust some things and you just kind of look and you go with your gut, right? And say, oh, I think I can remove this one. You have a look, no harm, no foul, right? You're gonna pull some things out, you're gonna add them into your model, and then you're gonna land on a model that you're comfortable with, right? There's really no right or wrong as long as you're not overfitting your model, right? And you're comfortable with where your R squared is. Right? So you can always tweak your models, right? But overall, there's really no more rules to follow, which is tough, right? Because we like rules, probably. Okay, if that happens, I'm going to do this. If that happens, I'm going to do this. Right? And so it's more about developing that feel for, oh, I think I could remove this one because I see a relationship here, right, that I could probably tweak a little bit. So we should use the adjusted R squared to assess the fit of our model. And I'll add here that the adjusted R squared takes the number of predictors, takes the number of predictors into account. And makes sure that we don't overfit the model. Well, it doesn't, but we do. It makes, and makes sure we do not overfit the model, right? Have too many predictors in there. As a general rule, right, the fewer predictors that we need in our model, the better. Okay. So the fewer predictors we need in our model, the better. So that's just kind of a good rule of thumb, because like I said, as you add in more predictors, right, your R squared will get better, your model will improve, right? But it's going to be a trade-off with how much did it improve over having that many predictors, right? And so it's going to be this kind of trade-off scenario. Okay. So let's go back to our output here and talk about. So here, in the simple regression case, right, where we'll only add one x, one y, we said that the t-test, right, for the slope was going to give us the same results as the Anova, right? And so the f-test in the Anova just says, oh, is there anything going on in here, right? Essentially, is the slope different from 0? Now, like we said, these lines, right, so this first line, the points for line, is going to be assuming that nothing changes in the points against line. Right? And the points against line is assuming that nothing's happening in the points for line. Right? So these are individual things. So these p-values are only attached to the points for, assuming everything else stays the same. And so even the order that we put these in could change things. And so, but we'll get there, right? And so here, these p-values are for the individual coefficients, right? Is this individual coefficient significant? Yes or no? Right? Is it adding to my model? The Anova now, because we've got multiple coefficients, right? The Anova is just giving us a quick overview. Are there any coefficients in here that are going to contribute to my model? It's not going to tell us which one, right? But it's just going to look and say, hey, is anything helping here, right? And so the Anova is actually usually the first one that we look at, right? And did you guys do Anovas just for t-test pairwise comparisons of means? Probably, right? Yeah, maybe just a very little. Yeah, right. But the Anova always just kind of does the same thing. It just has an overview and says, "Hey, is anything going on in there?" Right. And so a significant Anova is going to say, "Yeah, something's going on. You should probably go figure out what it is." Right. Same thing for the means. If you're comparing the means of 2 or 3 or 4 groups, not 2, but 3, 4, 5 groups, the Anova is just going to say, hey, are any of you means different from each other? Cool. Then you go in and if you get a significant Anova. And so here, right, we've got the significant Anova that says, yeah, something's going on. We already looked at what was going on, right? But typically as a first step, you look at your scatter plots, see if something might be going on. Then you can run an Anova and to see, is there anything statistically significantly going on in here? If you get a p-value that you can't reject in here, right, 0.19 or something weird, then you're not going to build a model off of those predictors, right? Because the Anova already said there's nothing here, right? There's nothing in here that's going to help you predict y.
So is it correct to say when you do your multiple regression, you look at first the ANOVA, and let's say, for example, your ANOVA says it's not significant.
Yeah.
So that's the time you go to your multiple regression up there and look for a variable that is the p-value is greater than 0.3. Something like
Yeah. But for the ANOVA to be insignificant, there would have to be nothing going on. So
okay.
that would mean that all of these would be insignificant as well. Right? And so, so if we get a significant ANOVA, then that would give us the case where one of them might be insignificant, right? And so we probably pull it out. Usually, I think we move it to the bottom. I have to refresh on that, but I think we move it to the bottom of the pile, and then we pull it out if it's still insignificant. Like that. Stay tuned. But yeah, so this p-value is going to tell you, let's talk about it, or let's write it down. So the ANOVA for multiple regression tests, because sometimes I find it helpful just to see it in terms of the null hypothesis, right? And so it's going to test that beta 1 is beta 2 equals beta 3 equals da 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 da. Oops. Equals beta k, and they're all equal to 0, right? Nothing's going on. No significant predictors whereas the alternative hypothesis is not necessarily that they're not all equal to 0, right? It's just that at least one beta I is not equal to 0. Meaning there's at least one that you need to hunt down and find that will help you model your y. So this is saying that there's at least one significant predictor. So what we do is, after looking at our scatter plots, right, to even suspect that there might be a relationship, right, you want to be able to say, oh yeah, well, this is the reason that I thought there might be a relationship here. You're not just going to go in blindly and just throw them all in, right? And so after looking at the scatter plot, and selecting possible predictors, so after figuring out which ones are possible predictors, then we run an ANOVA to see if any of them might be significant. We run an ANOVA to see if any of them are significant. I'll say in modeling Y. Right, in modeling. I can never remember. I think 1L for modeling is the American way, and I should do it probably the Canadian way, 2 L's. Doesn't matter. Might be the other way around. I can never remember. So, yeah. Either way. Right, so you run the Anova. I would say the Anova is not that helpful if you've crammed 40 variables in there, right? The Anova saying, yeah, there's one in here that's going to help you out. It's not very helpful, right? So I would probably start with my core ones, and then, you know, you should see something significant, and then you can kind of go from there, right? And so just have your usual suspects, let's call them, right? Throw them into the Anova. You don't want to overwhelm your Anova either, right? So, yeah, just keep in mind that the use of the Anova is not to tell you what's going on, it's to tell you if there's something going on, right? And so it's to save you a lot of work, right? And so because you've probably done more work with means, right? Comparing the mean of group 1 to the mean of group 2. If we're comparing 5 means, right, then your Anova would say, well, the mean of group 1 is equal to the mean of group 2, 3, 4, and 5, right? They're all equal. So then if you say, well, all these means are equal, you're not going to go in and do pairwise comparisons, right? There would be so many. There's no point. The Anova already said, hey, don't do it. There's nothing going on in here, right? If your Anova comes back and says, yeah, there are at least 2 means that are significantly different from each other in here, then you go in and you deep dive and figure out which 2 means are significantly different from each other. Same idea here. The Anova is looking at these coefficients. Are there any that are significantly different from 0? Yes or no? Right? No, they're all equal to 0. Well, don't bother. It's not going to help you predict anything. Or, yeah, there's one in here that's going to help you out. At least one that's going to help you out. Yeah.
Yeah, but Anova will say at least one, but it will not specify that there are
That's
2
right.
or more. Right?
Yeah. So then you go on and you do your, so that's when you look at this output here. And that's when you need to look at your individual coefficients and their p-values. And so if we have a significant Anova, if we have a significant Anova, we look at the model output to determine which coefficients are significant. Which coefficients, like, or slash predictors, are significant.
I'm trying to feel. So if you go back
to the output?
Yeah.
Yeah.
So p-value for Anova is significant, right?
Yes.
So it means at least one is a significant predictor.
Yeah.
Okay. So
at least one of these
are
is helping predict the means.
But both of them are significant as well.
That's
I mean,
right.
the p-value.
Yeah, so in this case, both of them are significant.
Yeah.
But this is saying that only one has to be significant.
Okay.
So in this case, yeah, they're both significant, so that's good. Right. But this one, all it's saying is that at least one of those will be significant if you have a look at them individually. So we could even have a situation like this one is maybe 0.21.
Yeah.
Not significant, right? But as long as this one is really small, right? As long as this one's significant, we would still get a significant value down.
Which is why this p-value isn't significant when all of them are.
That's right. Yeah. So it's just trying to save you a little bit of work. Although it's tricky, right? Because we built the model already. So for us now, it's not that much work, right? Because we've got computers, and so computers just give us all of this all together, right? And so for us now, it doesn't really make sense anymore, right? But imagine back when you didn't have a computer and you had to do this by hand, right? Then this is going to be a lot easier to calculate, right? Because knowing Claudia probably made you calculate the sums of squares and all that kind of fun stuff, right? And so tedious but doable, right? And so being able to determine if I should even bother in fitting the model, right? That's going to be a huge time saver. So I would argue that now, no, we don't. We can just fit the model and look at the model summary, right? This is kind of a remnant from before, but it is kind of helpful to say, well, I had a significant Anova, and so then I continued and I looked at my actual output from my model, right? And so there's a lot of stuff like that where we look at the Anova first, only because it used to save us time. Now it's just going to be an argument that, yes, at least one of these things is helping us out. Does that kind of help? So it is a little bit like, why would we've already got both of them, right? So why would we care about the Anova? We don't really, right? It's just an argument that says, well, because I had a significant Anova, now I can care about these individual predictors. So it is a little bit backwards, right? But it's just how it is. So, all right. Where were we here? Okay. If we have things from two different groups, right? What we can do, so this is narrowing it down to two groups, right? Some binary variable, right? 0, 1 typically. If we've got two groups that we want to compare, right? The first option, right, would be to put that binary variable into our model. We're allowed to do that, right? So far, we've really only kind of talked about quantitative variables, right? So numerical variables going into our model. Our response is still going to be numerical for now, right? But now we're making room for numerical and categorical predictors, explanatory variables. Yeah. And so when comparing two groups, we code the categorical variables, right, as indicators, right, 0, 1 indicators. So when comparing two groups, we can code the categorical variable using 0, 1 indicators. right? Male, female, for example, right? If it's in the male category, let's make it a 0. If it's a female, make it a 1. Raw, raw, raw. It could be the other way around. How about this? Doesn't matter, right? But you're going to feed it a 0 into your model if it's a, let's say, a male, right? And a 1 into the model if it's a female, right? So that's going to adjust your what. So if we focus on just 2 variables, so if you've got your y hat is b0 plus b1 x1 plus b2 x2, right? Where x2 is an indicator variable, right? If we let x2 be an indicator variable, then x2, we're only going to be able to feed it a 0 or 1, right? 0, this term goes away, and then we're just left with a simple regression, right? 1, well, 1 times my coefficient of x2, that's just going to get mushed with my intercept, right? So it's just going to change my intercept, but my slope stays the same. Right? And so, right? So if x2 is 0, right, then we get y hat is b0 plus b1 x1, whatever that is. I'm dropping the error terms. I'm being a little bit lazy that way, but I do find that they cloud what we're talking about too, so just pretend they're in there. If x1 is 1, then you get y hat, oops, is b0 plus b1 x1 plus b2 times 1. Oh, yeah, thank you. Just checking. Make sure you're paying attention. I'll always say that. So then your intercept would be b0 plus b2, right? Combining your like terms, and then plus b1 x1, right? This is saying that the intercept has changed, right? So it has a new intercept. But it has the same slope as when x2 equals 0. Okay. That's right. So they would both boil down to simple regressions. Right? I would go for the adjusted R squared, just so I'm not being overly confident in my model, right? And so, because the reason I say that is because this slope is not the slope for just when x2 equals 1, right? Or when x2 equals 1. It's for both values of x2, right? And so this slope uses all values of x2, right? So it uses all the data, right? Not just the indicator that's turned on at that point. Right? And so the slope is built using all values in the data but will be the same for each of the categories being modeled. But will be the same for each category being modeled. So that's good, right? But wouldn't it be so nice if we could have different intercepts and allow for different slopes, right? Because they don't necessarily have the same slope, right? They're not necessarily running parallel to each other, right? So to allow for different intercepts and different slopes, we use, the words escaped me, interaction terms. I knew it was another I term. Okay. So an interaction is going to be between two variables, and that's when we just multiply them when we plug them into our model. So it's going to look like this. So to build a model that allows for different intercepts and different slopes, for different intercepts and different slopes, for each indicator, we use an interaction term. An interaction term is an interaction between, so here, right, our x1, we haven't talked about what it might be, but whatever x1 is, right, it can interact with our x2. Right? And so what we have is we build off of this model that we had, and so we can say that, well, y hat is beta naught plus beta 1 x1 plus beta 2 x2, right, plus beta 3 of x1 times x2, right? Where x2 is still going to be an indicator variable. Where x2 is an indicator variable. So this here is the interaction term. Oops. Interaction term. And just like we added those variables in onto our simple linear regression, right, in the LM command, right, you've got y tilde, your x1, your x2, so plus x2, plus, and then x1 times x2. Right? So you just plug them in, and that's going to allow for different slopes and different intercepts at the same time. Okay. Let's see here. What else did I want to talk about? So that's the interaction term. I was convinced I'd be out of time. Let's see if I can find. Did I maybe make a note here? No, I did not. Just on the exercises that I want you guys to work on. You guys are running me ragged. You want class, no, you don't want them, but class assignments, lab assignments. I'm like, they're all going to be in R. I don't know what the problem is. So I decided I should probably pick some problems. And so these are just out of your textbook, but from chapter 2, and I'll just copy them here into our notes maybe. Put it in there. And then I also want this one. Just a little, I know, don't be disappointed that it's a short assignment. Let's call this assignment number 1. What I'll try to do is I'll try to give you just short little assignments after each class, right, to kind of emphasize what we talked about in class, right? And so I did go back because 2.13 introduces the brain pH data, but just like before, right, the brain pH data is in the Stat2 data package, which you have, so you can just access the data. I want these done in Markdown, of course. And so show your output, show your code. So use Markdown. Show output and code, of course, right? I want to see everything. Justify all your answers, right? So here, justify all your answers, of course. Right. And whether you want to submit it as an HTML or as a PDF, it doesn't matter to me, right? But just make sure it looks good, right? And so HTML or PDF, whichever you prefer, by email. Give you guys a week. What's a week from now? Are we in February? Wait, what did you say? Oh, I wish. We'd be out of here so fast. I think Monday is the 3rd, right? Yeah. So.
Yeah, we have a 7 p.m.
Sure.
What's it?
Wednesday the 5th? Sold. Wednesday, February 5th. Here, this is just playing around and applying what we did just today, right? And so here, they measured the pH in brain tissue. I know. Yikes. But it was the only one that kind of touched on exactly what we did today. And so of 54 persons, one possible predictor of brain tissue pH is age at the death of the person, right? So this is from chapter 2. Remember, chapter 2 is just simple regression, right? So we're just talking about age. Is age a good predictor of pH? And so it tells you what the data set is called, brain pH, and then produce a scatter plot of the data. So of course I want to see the scatter plot, nothing crazy here. And you can use base plots, right? You don't have to use ggplot or anything like that. Does there appear to be a linear relationship? Should have that one in the bag. And then test the hypothesis that there's a linear relationship between pH and age. Does this confirm your suspicions from part A? Explain, right? And so lastly, we talked about 3 different ways that we could test if there's a linear relationship, right? Is the slope significantly different from 0? You can have a look at the Anova output, which is going to tell you the same thing, or you can look at the correlation, right? And so we talked about a couple of different ways that we can test if there's a linear relationship, right? And so those are those things. And then we introduce the study of brain tissue, blah, 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 the data in the blah, blah, blah. Are age and sex a good combination of predictors of pH, right? And so now we've got 2, but the sex variable is going to be an indicator variable, right? And so we'll just start there with an indicator variable, right? Kind of turning on, turning off the different intercepts, and that's all it's doing. Things got weird here, but whatever. Make a scatter plot of pH against age. Again, with sex as a grouping variable, right? So somehow, some way, you're going to figure out how to identify on your scatter plot which ones are males and which ones are females, whether that's different colors or a different symbol for each. I don't care. Get creative. Okay. And then comment on the plot. Basically, what does it look like? Fit the regression of pH on age and test whether there's a linear association between the 2 variables. We actually did that already. And so because you already did that in question 2.13, let's call it. Otherwise it gets confusing. But then I want to fit a model that produces parallel regression lines for the 2 levels of sex. Write down the fitted prediction equation for each level of sex. The parallel lines, right, have the same slope. But then I'm adding part D. Now use an interaction term to allow for different slopes. I guess I can move this down. Use an interaction term to allow for different slopes. And then write down the regressions. But you will do that.
But the other variable is sex, right? So it's just 0.
Yeah. Oh, because the other one is age. Yeah, because age is going to be in there, right? And so fit a model that produces parallel regression lines for the 2 levels of sex, that's on age, right? So assuming age is, so age is X1. Oh, nice. Any questions? So I'll post this one as a separate document, but I'll just pull it from here, right? And so you'll have access to it, but otherwise it's at the end of these notes here. Yeah.
Okay, make sure you're going to us R because we are seeing a lot of R.
So yeah, because it's an applied course, right? So we need to know how to use R. Of course, that's really hard to test in a test situation. And so in a test situation, I can give you the output and then you have to know you have to answer questions based off of it, right? So I would have to give you all that output with none of the write-up and then you'd have to write around it, right? So in a test, no, I don't expect you to be able to produce kind of output on a timeline, right? But part of this course is producing this output and just kind of being able to interpret it. But for the tests, no, it's going to be just interpret.
Not code.
No.
So it will be multiple choice or
Yeah, I'll get closer to a test, which I know is kind of coming up. I'll give you guys a practice test, but also like a breakdown of what to expect, right? Whether it's multiple choice, long answer, that kind of thing. But I'll have to make the test to be able to give you the inside scoop. It's always better if I make it first and then tell you about it than if I tell you about it and then I make it. So, any other questions?
Let's say there will be variables x1, x2, and x3.
Yeah.
X2 is dependent on x3. So you don't want x3 in your model.
Yeah.
And to know the relationship between x2 and x3, you draw a scatter plot between x2 and x3.
Yeah.
And if it looks linear or there is any shape it shows.
Yeah. Then you could probably remove it, or like replace it with just the one. Usually.
Scattered all around.
So then they would be independent, right? You could use them as if they're independent.
So there are 14 variables, then you have 14, 28.
You'd want to break it down. You can use that plot of the data command, and it just gives you all those scatter plots, right, that we saw last day. But if there's a lot, then it's hard to see. So then you might want to break it down a little bit. All right. See you guys in H116A. Meet you over there. Mm-hmm.